I'm very glad to present our speaker today, Pavel Sukhachov. He is my collaborator. He got his master's degree from my alma mater, Taras Shevchenko National University of Kiev in 2014. He did his PhD in a record time of less than 2 years and finished it in 2016. He was a postdoc at Western University in London, Ontario from 2016 until 2019. He is a postdoc since last April. Last April means 2019 at Nordita. And he is going to join Yale University as a postdoc starting in fall. So today he will be talking about electron hydrodynamics, and I'll give the microphone to him right now.
Yes, thank you. Thank you very much, Igor for a nice introduction. It is a great honor and pleasure to give this colloquium today. I'm grateful for the opportunity. So today I would like to talk on electron hydrodynamics in solids. During my talk, first I'll outline basic notions of hydrodynamics for those who are not familiar with the field. Also introduce some history of this field. Next, I will give a brief, quite brief but quite long overview of electron hydrodynamics in solids and its experimental manifestations and observations. And finally, in the final part of my talk, I will consider hydrodynamics in Weyl semimetals and give a few examples of particularly interesting consistent hydrodynamics, where there is an interplay of non-trivial topology and electron flows. So let's start with basics of hydrodynamics, where I outline the key notions that will allow us to stay afloat during this talk. So the key definition, the general definition of hydrodynamics is that hydrodynamics is a microscopic theory that studies the motion of various fluids, such as, for example, water, gas, etc. Hydrodynamics is a very old field. Probably it starts from Archimedes before Christ. However, its key notions that are quite similar to those that we're using now were formulated during 17th to 19th centuries by such well-known mathematicians and physicists as Leonhard Euler, Daniel Bernoulli, Claude Navier, and Navier-Stokes. So, what is hydrodynamics? Hydrodynamics is a theory of conserved laws. It's based particularly on the conservation of momentum, mass, and energy. Its key variables are, of course, fluid velocity, which is a primarily variable of all hydrodynamic theories. Also, particle density and energy density are very important quantities. The key equation of hydrodynamics is, of course, the equation that describes the evolution of fluid velocity. In particular, this equation is known as Navier-Stokes equation. It's a Navier-Stokes equation for a simple fluid, textbook fluid, is given as follows. First term of this equation, as you can see, describes the time evolution of the fluid velocity. Also, there is a nonlinear advection term which combines both fluid velocity and derivatives. There is also this term which corresponds to forces that act on fluid. Of course, there is a term related to friction, and which is known as diffusion term, and coefficient here is known as a shear viscosity, which is explained in this cartoon. Essentially, shear viscosity appears when there is a friction between different layers of fluid that flows through, let's say, a pipe or near some boundary. And finally, the final term is related to compressibility of the fluid, where the corresponding coefficient is known as a bulk viscosity here. And essentially, it appears when fluid expands or contracts. It is important to underline that Navier-Stokes equation is a nonlinear equation. As you can see here, there are nonlinear terms. As therefore, in general, it is quite hard to solve it analytically. And even numerically, there are quite a few problems with its solution, in particular range of parameters, which I will briefly outline below. The other equation that is also important is a heat transfer equation, which describes the evolution of the entropy density. It's written as follows. As one can see, there is also advection term. There is term related to the thermal conductivity. There are also terms related to friction. Here, for example, shear viscosity, and this term for the related to the bulk viscosity. Yes, such equation is a little bit more complicated than Navier-Stokes equation, and is also nonlinear, as one can see from these terms, for example. And finally, another equation that is needed to describe a simple hydrodynamic system is a continuity equation that corresponds to the conservation of particle current density. And it's written as here. Heat transfer equation is particularly important when we consider such process as, for example, combustion or burning. Here, for example, one can see the cartoon where two gases, one is cold and one is hot, intermix. And of course, both fluid velocity and heat transfer play a very important role in such process. As I said before, hydrodynamic equations are nonlinear. Therefore, they allow various regimes where one particular term dominates and the other are irrelevant. In order to characterize all these regimes, usually people introduce quite a few dimensionless numbers that are known by the names of the people who introduce them. Among the most well-known of such numbers is the Reynolds number, which is essentially the fraction of advection term to diffusion term, and it explicitly shows us whether the viscosity effects are important in such a system or not. Indeed, after some writing of this term, one can get a simple expression where the Reynolds number is proportional to the fluid velocity and system size, but inversely proportional to its kinematic viscosity. So here, of course, we can separate two main regimes, where first regime is a regime where the viscosity dominates. In such a case, Reynolds number is very small, since the diameter dominates, and it is known as a layered flow. In such a case, one can neglect the nonlinearities, and in principle, it's quite easy then to obtain the solution in a closed form of Navier-Stokes equation. On the other hand, there is another interesting and very important for practical applications regime, which is known as a turbulent or chaotic regime. It is characterized by a large Reynolds number. Such regime requires a solution of Navier-Stokes equation where nonlinear terms are taken into account and can show a wide variety of interesting effects. Among them, for example, I would like to mention famous von Karman vortex street. Essentially, it appears when a fluid flow interacts with an impurity. For example, here, flow goes from the left to the right. And in such a flow, vortices start to appear, which oscillate with some characteristic frequency. Another textbook example of turbulence is, for example, a submerged stream. Here, as one can see, there is some fluid, which is shown by this cyan color, which is pushed through the other fluid or even to some kind of empty medium. And turbulent or chaotic flow is clearly evident here where some irregularities appear. Of course, there are many other examples of where very interesting turbulent behavior of the fluid, but it will take more than one talk to even just show them. So, hydrodynamics, as we already understood, is a very vast field. It includes many different subfields, such as aerodynamics, magnetohydrodynamics, geophysical fluid dynamics and meteorology, hemodynamics, and many others. The range of system scales is as small as femtometers for example, collisions of heavy ions, where hydrodynamic description is also applicable. it includes meters and kilometers for our usual objects such as waterfalls or water streams, or it can even extend it up to astronomical length scales such as parsecs, or where the motion of galactic gas or, for example, accretion to the black hole are also described hydrodynamically. So the bottom line is that hydrodynamics is able to describe a wide variety of systems. However, recently, huge source of interest, both experimental and theoretical, was directed towards an unusual manifestation of the electron hydrodynamics in such seemingly opposite to a fluid system as a solid. So could it be the case that we can have some hydrodynamic description of solids? And the answer is yes, since we have a lot of quasi-particles inside our solids. And these quasi-particles could, in principle, allow hydrodynamic description. And this would be the key message of my second part. So, in general, we can separate our transport regimes in solids into two main groups. So the first one is, well, non-hydrodynamic regimes, which include such transport regimes as, for example, ballistic, where electrons move freely from one system surface to another and do not interact with each other or with impurities. This regime is quite interesting since it was believed that it is able to realize the highest possible conductivity. But as I will talk a little bit later, it might not be the case. The other regime that is omnipresent in all common bodies is the ohmic regime, where electrons interact constantly with impurities, phonons, and constantly scatter their momentum. In all such regimes, the momentum relaxing length scale, essentially the ohmic regime, is the smallest length scale of the system. However, in 1960s, Radi Gurzhi asked and answered the following question. Could it be the case that in some system, we can have a momentum conserving length scale, such as electron-electron collision length scale, as the smallest length scale of the system? In such a case, electrons will interact frequently between themselves and form a fluid that resembles a flow of viscous fluids such as, for example, honey or even water through a pipe. As you can see from this cartoon, here the momentum relaxing length scale should be the largest in the system, and momentum conserving electron-electron interaction length scale should be the smallest length scale of the system. And this regime is essentially a regime which is similar to flow of a fluid. It's called hydrodynamic regime. As was shown by Radi Gurzhi, this non-conventional hydrodynamic regime will allow to quite interesting effect, which is related to the dependence on the resistance on temperature. So let's consider this cartoonish description. At small temperatures, we can have a ballistic regime in our solid, where the effective length scale is determined by the size of the system. Therefore, the resistance of our material will be inversely proportional to the effective length scale and almost insensitive to temperature, but inversely proportional to the system size. Physically, in such a case, electrons move from one surface to another and scatter similarly like this process. However, Radi Gurzhi showed that in some finite window of temperatures, it might be the case that electron will move as if a particle undergoes some diffusion through a fluid. So essentially, electrons diffuse among themselves, but do not relax their momentum, unlike ohmic regime. In such a case, one can estimate the effective length scale as follows, just by using a usual law of diffusion. Such an effective length scale is proportional to the system size squared, but inversely proportional to the electron-electron collision length scale. The latter essentially depends on temperature, and this leads first to a different dependence on system size. This system size squared compared to linear ballistic regime, and decrease, and it also leads to the decrease of the resistance with temperature. Essentially, this decrease of the resistance with temperature in hydrodynamic regime of electron fluid is known as the Gurzhi effect now. Of course, when temperature rises, electron impurity collisions could become important, and finally, electron-phonon interactions will take place, and our resistance will start to grow. Now, it is a question of numbers. Could it be indeed the case that electron hydrodynamics can be realized in real solids, and this window is large enough to allow for an experimental observation? Or we always see something like a direct transition from ballistic regime to electron impurity collisions? Until 1990s, the answer to this question was unfortunately negative, and scientists were not able to find any signatures of hydrodynamic behavior even in pure, at that time, materials. However, with the advancement of technology, pure materials appeared, and new methods of transport measurements also allowed to pinpoint the Gurzhi effect in aluminum gallium arsenic heterostructures in pioneering works by Molenkamp and de Jong. Almost 20 years later, viscous contribution to the resistance in such two-dimensional metal as palladium cobaltate was observed by a group of Philip Moll, published in Science. However, the field of electron hydrodynamics came to its flourishing with the rise of graphene, which can be made sufficiently pure with sufficiently low electron-phonon interactions. There are a wide range of various interesting effects related to the formation of electron fluid was observed. Among them, I just mentioned such effects as negative nonlocal resistance, higher-than-ballistic transport, Poiseuille flow manifested in an unusual hollow field profile, breakdown of the Wiedemann-Franz law in Dirac fluid regime, and many others predicted theoretically. In the follows, I will mostly concentrate on the effects that are both theoretically established and experimentally verified. So, let's start with one of the classic now effects related to the formation of the electron flows in graphene and other heterostructures. This effect is related to the formation of backflows. So imagine that we have a so-called vicinity setup of graphene. So this is a graphene sample. Here we have a source of electrons. Here we have a drain of electrons. And electrons, if we turn off the viscosity of electron fluid, which is possible in numerical simulations, which I am showing right now, it is possible to get this figure. So our electrons start in the source and end in the drain, form quite trivial patterns. And the distribution of the electric potential is also trivial. Of course, it is positive near source and negative near drain. However, when we include the viscosity of electron fluid, the picture qualitatively changes. First, we observe formation of electron vortices in the vicinity of source and drain here, as we can see. Next feature is the formation of negative potential regions in the vicinity of source and an opposite side near the drain, of course. The formation of these negative potential regions allowed to introduce the so-called negative non-local resistance, which of course a little bit misnomer because resistance can be negative. But essentially this is just a potential difference measured between some point at the surface and let's say 0. And as we can see, compared to the case where the viscosity was neglected, this quantity, this quantity resistance can change its sign, as we can see here. Experimentally, that effect was observed in graphene, as shown in this diagram. So here I'm showing the density plot in plane of electron density and temperature. And this blue long shape bars correspond to negative local resistance. You can see it becomes negative for a finite range of temperatures and for some finite range of densities, doping densities. The formation of, and this negative local resistance was, of course, attributed to the formation of electron fluid inside graphene. One of the hallmark features of the electron hydrodynamics is that it appears at a finite range of temperatures. So the temperature should not be very low because then impurities will become very important, and electroviscosity will not dominate transport. But it shouldn't be very high because then the electron phonon scatterings will dominate and ruin all hydrodynamic description. A little bit later, this effect, essentially the formation of the negative potential regions, was observed with scanning microscopic technique in this paper. They indeed showed that in the regime where the electron fluid forms, the regions with negative non-local resistance are formed in the vicinity of contacts here and here. The other interesting effect also related to the formation of the electron fluid in graphene constrictions is the so-called higher-than-ballistic flow predicted theoretically by a group of Levitov and Falkovich.
Pavel, can you pause
Yes.
for a second? We have a question. Maria, you want to ask? Unmute yourself and ask.
I'm sorry, a very short question. Those densities that you showed in the previous slide, how are they compared with the half filling in graphene? So is it the sample is really doped or is more nearly undoped?
In all these cases, samples are either electron or hole doped. As far as I can remember these experimental papers, they were not able to reach zero exactly. So they were mostly until this line. So this red part, as far as I can remember, was not accessible.
Okay, thanks.
So yeah, these studies were mostly done in the Fermi fluid regime, where the chemical potential is quite noticeable. I will talk a little bit briefly on Dirac fluid later. So electron flow in constriction. As was predicted by a group of Levitov and Falkovich, and very interesting effect can appear in a graphene constriction, whereas graphene constriction. So compared to the ballistic regime, which is generally believed to be the regime with the highest conductivity, is the regime where the electron fluid forms might be characterized by even higher conductivity. Theoretically, this effect was explained by the fact that in the hydrodynamic regime, electric currents bundle together, as you can see here, and bypass the region near the edges where the momentum dissipation primarily occurs. Also, one can see from this cartoon, from this plot, which is essentially a perpendicular slice of this constriction. In the viscous hydrodynamic regime, the current forms a characteristic Poiseuille-like profile, parabolic-like profile, as you can see here, and it avoids the edges. Therefore, the majority of the current flows through the middle, through the center of the sample, and that's why the dissipation could be lower than in the case of the ballistic regime, where the current is almost homogeneous inside the constriction. Experimentally, this effect was measured almost the same year. Probably they were already doing experiments when they published the theory paper. So the group of GaAs use the following device. Here one can see a graphene sample, it's quite long, with several gates of different thickness, different widths. By fixing, for example, one gate, they measured a point contact resistance, essentially the voltage between, let's say, this contact and this contact. It was shown that at some range of temperatures, the point contact resistance of this gate can be indeed lower than that obtained from naive ballistic consideration, shown by thick lines. Of course, there is some dependence on the doping of this graphene sample. And this decrease of the point contact resistance comparing to the ballistic regime was attributed to the formation of the electron fluid and higher than ballistic flow through the constriction. However, this effect mostly corresponds to the total integral flow, and the formation of this viscous profile was not explicitly shown. That was understood at the time, and the same group, collaborating with their colleagues from Israel, attempted a different kind of experiment, where they tried to visualize the flow inside the sample by using a two-dimensional sample, which has the following form. Looks like a two-dimensional sheet, which is long in one direction and quite short in the other, and so-called single electron transistor technique. This group was able to map magnetic field around the sample, and then from this measured field, they reconstructed the current distribution inside graphene sheet. And they found quite interesting result. So for the longitudinal current, the current was both parabolic-like in ballistic and hydrodynamic regime, as one can see here. Of course, the curvature of the longitudinal current was much larger in the case of hydrodynamic regime, as you can see, comparing these two plots. However, qualitatively, the currents were the same. This could be attributed to the specifics of the electron transport in perpendicular magnetic field. However, they found that such quantity as a whole field, essentially its Y component, is also sensitive to the longitudinal current and could be used to map and distinguish ballistic and hydrodynamic regimes. As one can see here, in the case of ballistic regime, the whole field is very flat. However, in the case of hydrodynamic regime, it follows a parabolic-like profile. By using experimental techniques as well as numerical calculations based on Boltzmann theory, the phase diagram was obtained, and the results were overlaid on this phase diagram obtained numerically. So here we have four main regimes that depend on the interplay between the electron-electron collision lengths and momentum relaxing mean free path. So in the upper right corner, we have a ballistic regime where the momentum relaxing length scale is the largest in scale of system, as well as electron-electron collision length is the largest. So electrons do not interact with impurities and do not interact between themselves almost. In such a case, we have curvature of the Hall voltage, which is either zero or even becomes a little bit negative. We can have also an ohmic regime where electrons interact with impurities. Here we can have slightly non-zero curvature. And we can have porous regime where electrons both collide with impurities and with other electrons. And finally, we have our Poiseuille regime where electrons collide primarily between themselves. So momentum relaxing scale is large and momentum conserving electron-electron collision scale is small. And in this case, the curvature of the Hall voltage is large, as you can see. Next experiment, which is also widely used now as a signature of electron hydrodynamics, is related to the violation of the Wiedemann-Franz law. Indeed, let me remind what it is. So Wiedemann-Franz law states that if the heat transport and electric transport are done by the same channels, by the same quasi-particles, then the ratio of the heat conductivity to the electric conductivity is a number which is known as the Lorentz ratio. And usually in the Fermi fluid regime, Wiedemann-Franz law holds quite well. However, in the case of so-called Dirac fluid, which essentially appears in the vicinity of the charge neutrality point in graphene or another Dirac material, electrons and holes play the same important role, but they contribute differently to the heat transport and to electric transport. So for example, for the heat transport, they flow in the same direction, but for electric transport, electrons and holes move in the opposite direction. That's why it might be the case that they undergo different scattering processes. And that's why an imbalance could appear in such channels. Experimentally, the signature of this Dirac fluid regime and the breakdown of Wiedemann-Franz law were measured in graphene, as we can see here from this figure, where we have temperature on the y-axis here and density on the x-axis here. So near the charge neutrality point, so we can follow this direction, at some intermediate values of temperature, we have a strong violation of the Wiedemann-Franz law, almost 20 times. And since the violation appears at finite range of temperatures, it was attributed to the formation of the Dirac fluid and linked to electron hydrodynamics too. Indeed, when the temperatures are small, then the impurities and defects play a very important role, and that's why hydrodynamic regime is not applicable. And the same goes with the higher temperatures where phonons start to dominate and rule in this regime. So far, I was talking mainly about effects where the nonlinearities are not important. Therefore, the main question could be presented as follows. Is it possible to have various nonlinear effects such as turbulence, formation of different vortices von Karman streets, for example, in graphene? Unfortunately, the results of this paper states that in real materials, it might be very hard to reach such a regime. However, numerically, we can indeed simulate graphene with a with quite large Reynolds number. Even for Reynolds number 25, which is not that large for dimensional material, we can observe some signatures of the preturbulent regime in graphene. So here, for example, I'm showing the picture at the beginning of the pumping of this current through the constriction. So we have constriction here, and our current first goes along straight line, it's laminar, but then after some time, instability appears and currents become chaotic. So some kind of perturbance signatures appear. At very large Reynolds number, it was shown that vortex shedding can be observed in graphene after circular impurity. So we have a circular impurity here, and our current goes from the left to the right. And as I showed before in the first several slides, vortices can appear and could be tracked as could be tracked down to oscillations of electric currents through the sample. It was predicted that for realistic graphene parameters, the frequency of such current oscillations should be approximately in megahertz regime. So the key bottom line here is that in principle, turbulent regime, or at least preturbulent regime, is possible in graphene, but one still needs to improve the quality of samples and probably came up with larger samples. The next question that is worth also investigating is whether we can have a hydrodynamic regime in other materials, for example, three-dimensional materials, in particular Weyl semimetals. And the answer to this question is yes. There are signatures of electron hydrodynamics in Weyl semimetals too. As was shown in this paper, by using two contacts and a wire of a Weyl semimetal tungsten diphosphide, um, the resistivity of this wire could indeed show some signatures of electron hydrodynamics. Indeed, by using this setup, an etching wire, they were able to change its width. It was shown that at large temperatures, the resistivity was a constant function of width. This is, of course, something that we very well understand from school and from university, that resistivity is a characteristic property of a material. However, at small temperatures, they started to see a strong deviation of the resistivity from constant behavior. Resistivity started to depend on width of the sample as width up to -2 power. The other effect that they also observed in the same experiment was a strong violation of the Wiedemann-Franz law, where the Wiedemann-Franz where the Lorentz ratio reached the minimum observed in literature, probably 0.05. Taken together, these two effects were used to claim that hydrodynamic regime is also possible in Weyl semimetals. However, Weyl semimetals is a very specific system which has a linear energy spectrum in the vicinity of well-separated Weyl nodes. It has a non-trivial topology. Therefore, in order to describe such a system, we need a specific hydrodynamics that is modified to include these effects. And such a hydrodynamic theory was actually derived by us in these papers, and we called it consistent hydrodynamics. Since a very nice introduction to Weyl semimetals was already made during the talk of Professor Prof, I would like to just briefly outline the key properties of Weyl semimetals and move to original results related to electron hydrodynamics. So the low energy Hamiltonian that is widely used to describe the properties of Weyl semimetals in Dirac semimetals is as follows. It is block diagonal. It has Pauli matrices that correspond to spin or in general pseudo-spin degree of freedom. Here, the speed of light from relativistic physics is replaced by the Fermi velocity, and the sign corresponds to chirality. The energy spectrum of this Hamiltonian is simple. It has a form of double degenerate Dirac cone, where both party inversion and time reverse symmetries are preserved. If we break one of these symmetries, we can separate Weyl nodes in momentum space, for example, by breaking time reverse symmetry. The corresponding parameter is known as, for example, color shift parameter, which was discussed in view of interaction effects in this paper. Also, we can break a party inversion symmetry, which will lead to the separation of Weyl nodes in energy, as we can see here. Usually, in condensed matter, it is quite hard to have the crossing of energy bands, since they can always hybridize and open the gap. However, in Dirac semimetals, this is not the case because of additional symmetries that protect this crossing. In Weyl semimetals, it is the topology itself that plays this protective role and prevents opening the gap. Non-trivial topology of Weyl semimetals is quantified by quantity that is widely known as a Berry curvature. Berry curvature of Weyl semimetals has a following trivial form, it's monopole-like. So the Weyl node of positive chirality is a source, and a Weyl node of a negative chirality is a drain of the Berry curvature. Actually, this picture can be used to explain the topological stability and of Weyl nodes. Indeed, the total flux of the Berry curvature is zero through the whole Brillouin zone, since the surface that surrounds the whole Brillouin zone, due to its periodicity, is topologically equivalent to a point in the middle of the Brillouin zone. Therefore, if a Weyl node if a Weyl node of some kind of single chirality appear inside the Brillouin zone, it will lead to a non-zero flux of the Berry curvature. That's why it will change the topological number of Weyl semimetal, and that's why it's forbidden. However, we can create Weyl nodes of opposite chiralities inside the Brillouin zone, which will lead still to zero flux. And essentially, this statement is equivalent to famous Nielsen-Navier theorem that states that Weyl nodes of opposite chiralities can be created only in pairs. So we briefly underlined the key properties of Weyl semimetals, and now let's proceed to a theory that is able to describe their properties. The first basic step in the derivation of the hydrodynamic theory is a kinetic equation. However, since Weyl semimetals are systems with a non-trivial topology where the Berry curvature plays a very important role, one is to use a specific kinetic approach. This approach is known as a chirokinetic theory, which was first derived in works by Xiao, Niu made in 1990s, where they consider the motion of wave packets in some spaces with non-trivial Berry curvature. But it was later rekindled in high-energy physics community by Son Yamamoto, Stefanov In, and others who essentially formulated and refined the chirokinetic theory in the present form. So here we see the main equation of the chirokinetic theory, the Boltzmann equation. This is the equation that describes the evolution of the distribution function f lambda, where lambda stands for chirality. As we can see, this equation is quite complicated compared to a usual Boltzmann equation. We have, of course, Berry curvature that enters many terms in this equation. We have a renormalization of the phase space volume. We have an anomalous velocity. We have various anomalous effects here that act in the fourth term. Also, we have a collision integral, which is not that anomalous, but it is very important in solid-state hydrodynamics since it introduces the interaction of electron fluid with phonons and impurities. We can model the relaxation of momentum via a simple collision relaxation time approximation. In order to derive our electron hydrodynamics, we will consider small deviations from global equilibrium. Therefore, one can take the distribution function in its local equilibrium form, where we just need to modify the dispersion relation by including the terms related to the fluid velocity and vorticity, which essentially is a curl of fluid velocity. Then, by substituting these ansatz into the Boltzmann equation, and integrating it with momentum and energy, we can derive the key hydrodynamic equations such as Navier-Stokes equation and energy continuity equation. So in order to make this talk more accessible, I will just briefly outline the structure and key terms in this Navier-Stokes equation. In particular, here we have a fourth term, which includes electric field, magnetic field, also includes some vorticity effects. There are also anomalous terms here. There are terms related to dissipation. And the presence of these terms is particularly important for electron hydrodynamics in solids, since there is a preferred coordinate system in crystals, which essentially is the ion lattice, which should always be addressed. As for the viscosity terms, they can be added by hands in the Euler equation, thus transforming it into the Navier-Stokes equation. The energy conservation relation can be also written, and here I'm omitting quite a few terms related to gradients, which are not that important in the linearized regime, which will be mostly considered below. So here we see that right-hand side contains hydrodynamic term in current, CMU current, and current vertical contribution. And of course, as before, we can add viscosity and thermoconductivity terms by hand. I would like to underline that the energy conservation equation in solids is not that important when we do not consider large deviations of temperatures and large velocities, which is almost always the case. So if our velocities start to approach the Fermi velocities, then we, of course, need to introduce a Lorentz factor in our distribution function and take into account this equation. But in usual processes related to flows with small velocities, this equation plays a little role. The other important part of electron hydrodynamics are the expression for electric and chiral current. For those of you who are not familiar, this is a current, is an imbalance current between right-handed and left-handed quasi-particles. So currents looks quite complicated compared to what is usually used in literature. So in literature, usually people write only the first hydrodynamic term. However, in Weyl metals, the Chern-Simons terms that are related to the separation of the Weyl nodes in energy and momentum should be also included. Also, other terms related to the intrinsic conductivity, thermal gradients, gradients of the chiral chemical potential are also important. Chiral vertical effect term should be also there. Chiral magnetic term should be also there. Chiral separation effect can play an important role. Of course, systems can be different, and if a gradient of temperature is small enough, then these terms could be neglected. But general form of currents is as follows. These currents satisfy continuity relations, usual continuity relations, where the continuity relation for the chiral current is anomalous. And finally, this consistent current should be substituted into the Maxwell equation. I am calling this current consistent since it differs from conventional covariant currents that do not include these additional terms. And of course, I would be happy to discuss this in more details. However, our time is limited. Therefore, I will just briefly mention that in the case where the chiral shift and the energy separation of Weyl nodes are coordinate and time dependent, one should use a consistent current which will satisfy the continuity relation, unlike the covariant current which produces a non-zero right-hand side and leads to local charge non-conservation. So let me briefly illustrate how this framework of consistent hydrodynamics works. For this, I consider a simple setup, which essentially a slab of Weyl semimetal, which is infinite along z and x directions, but has a finite width along y direction. Of course, one can show that if hydrodynamic regime is applicable to the flow of the electron fluid in the slab, then the longitudinal current will have a classical Poiseuille-like profile, parabolic-like. However, the presence of the Chern-Simons terms will lead to a very unusual hydrodynamic anomalous Hall effect, which is essentially voltage between these opposite surfaces of the slab, which is modified both by the presence of the non-trivial topological term, this term, and hydrodynamic effects. So here, the interplay between these two terms is quite non-trivial. When the width of the sample is small, then this linear term, linear in the width term, dominates. Essentially, it follows the usual dependence. However, when the width becomes large, hydrodynamic term becomes important and partially cancels this term and leads to a change of the slope of the dependence of the voltage on the sample width. In principle, this change of the dependence could be accessed experimentally, and it would be a nice signature of the interplay between a non-trivial topology and hydrodynamic effects in Weyl semimetals. Another effect that could be used to probe and pinpoint a non-trivial topology of Weyl semimetals is a non-local transport in semi-infinite slab. So let's consider our sample, which is infinite along z and x directions, but is semi-infinite along y direction. We apply our source and drain of electric current along z direction, and that's why we expect our current to follow this swirling pattern. You can see here, the current will flow from the source to the drain. However, when the Chern-Simons terms are taken into account, then the field lines of this current become spatially symmetric, as one can see here, and the same happens with the electric potential distribution. As such, a non-trivial distribution of currents in principle leads to a characteristic magnetic field, which could be probed via this single electron transistor technique. So to summarize, in Weyl semimetals, there are signatures of a non-trivial interplay between both hydrodynamic regime and non-trivial topology quantified by the separation of Weyl nodes. Of course, there are other effects related to non-trivial collective modes, such as longitudinal and transverse anomalous Hall waves. There are also non-trivial effects related to the possibility of electron hydrodynamics on Fermi arcs. However, in this colloquium, I will omit them. And these effects, in principle, could be presented as a separate talk. So since this, I would like to proceed to my summary part. First, the first thing that I would like you to take home is that the hydrodynamic regime in solids is indeed possible for certain parameters which are experimentally accessible even with present techniques. Among the most interesting hydrodynamic phenomena in solids are the formation of vortices, negative nonlocal resistance, Poiseuille-like flow, breakdown of the Murchison rule, where one cannot just sum up the relaxation times related to the electron hole, electron impurity collisions, and the electron-electron collisions. Also, the breakdown of the Wiedemann-Franz law is widely attributed as one of the characteristic phenomena related to the formation of electron fluid. Further, I would like to note that in order to describe media that have a non-trivial topology, such as Weyl semimetals, one needs to use consistent hydrodynamics that includes both effects related to the Berry curvature and non-trivial topology. The interplay of the Chern-Simons terms and hydrodynamic effects is manifested in such an effect as a hydrodynamic anomalous Hall effect, where the voltage acquire a non-trivial dependence on the slab width. And finally, the Weyl node separation can be also manifested in spatial symmetry of the electron flow in the vicinity geometry, which is also semi-infinite slab geometry. I hope that more effects related to electron hydrodynamics, and in particular those related to three-dimensional materials, will appear in future. Thank you very much for your attention.
Thank you. Thank you for a nice presentation. There was a lot of information. So let me see if anybody has any questions. Let's see. I don't see a lot of question coming. Okay, there is at least one question. So Axel, please. Unmute yourself.
So yes, I have a question regarding the previous transparency, where you indicated that you had a magnetic field in the vertical in the z direction.
This is a chiral shift, so this is a separation of the Weyl nodes. This is not a magnetic field.
Right. So my question is, in this case, would you expect magnetic helicity to occur?
Good question. I'm not sure whether it will be noticeable. So there will be some what we had in this calculation is that some swirling patterns can indeed appear in the vicinity of sources, but they're quite sensitive to experimental parameters. So for the parameters that I'm showing, the swirling patterns are negligibly small. So I would expect that the corresponding magnetic field generated by these swirls would be quite weak. But in general, by taking into account these samples, these studies in graphene, I would expect that the magnetic field might be noticeable due to this.
Okay, yeah, thank you.
Okay, Renat, please.
Thanks for the nice talk. So a couple of slides ago, when you introduced the hydrodynamic equations, you said there are terms that are there basically because you have a preferred frame due to the ionic lattices. So I
Yes.
assume that this means that there are terms that are allowed if you break Lorentz and Galilean invariants. You don't have any such space-time invariants. Can you say a little more about those? Are they all known? What are they?
Yes, I understand that this question comes because usually in high energy physics, we just write energy tensor and calculate the derivatives from this energy tensor. Here, however, I followed a little bit different approach, which is still a textbook approach. By using the Boltzmann equation and integrating it with corresponding momenta, such as by calculating the corresponding momentum of the Boltzmann equation, for example, integrating it with momentum or energy, we can in principle identify all possible terms that appear in the system. So of course there are some gradient terms that I'm omitting here, but these terms is all that we have for our relaxation time approximation.
Okay, now I get it. Yeah, I see. So these are the standard terms in relaxation time approximation.
Yes,
And
yes.
they mush up all the lattice effects, basically. Okay, thank you.
Okay, Giorgio, you're next.
Thank you. Since you mentioned turbulence, can you see something like the analog of the Kolmogorov cascade here? And the reason I'm asking, and the reason this is potentially sort of new and interesting, is that the Kolmogorov cascade, usually it's broken by the viscous scale, right? You have vortices inside vortices inside vortices, and then gradients are high enough because of viscosity. Here, in principle, they could also be broken up by magnetization, since you have spin terms and you have coupling between spin and vorticity.
A good question, a good question. So far, I'm not aware of studies of extensive studies of the turbulence in solids. And the reason is that, as I showed before, the turbulent regime is quite unlikely to be realized in current experiments. However, I know that there are some studies of dynamo in three-dimensional materials, where people showed that it might be possible. But as for the Kolmogorov cascade, my answer would be, I don't know. I don't know whether it would be preferred or not, and which parameters one needs to have in order to realize it in solids.
Okay, Maria, you're next.
Yeah, Pavlo, thank you very much for a very interesting and you worked a lot to summarize. But I will come back to almost the same question as before with graphene about the Weyl semimetals. I'm worried about this Boltzmann approach because you know that this chirality needs to distinguish left from right, and I guess from Boltzmann you need the density, quite a high density.
Yes.
So for higher densities, in most materials, the two chiralities will be already like, you know, you will be over the Van Hoff singularity. And
yes, that's true. That's true.
Yeah.
Yeah, by using this cartoon, I can say that we cannot be exactly at this point. And of course, if we will be somewhere there, we will almost feel no chirality at all. So my statement is that in order for this framework to work, we need to be a little bit higher than these Weyl nodes, but lower the place where they overlap. So in principle, this approach can work somewhere there. I would say so. And in many materials, we have really well-defined Weyl nodes or Dirac nodes, such as, for example, cadmium 3 arsenic in some external field, or some materials such as transition metal half-Hessler materials in magnetic field. They can also have well-defined Weyl nodes where the energy window for linearized spectrum is high enough to allow for sufficiently high chemical potential, but still allow for well-defined chirality.
Thank you very much. So if I may ask another question first. say that you would not be able to use the Boltzmann approach. Is there any alternative to derive all these results that you have without the Boltzmann?
Yes. In principle, one can go and write a hydrodynamic theory as usually in high energy, starting from the energy momentum tensors that satisfies some symmetries. Also, one can try to work with something similar to Keldysh approach, some real non-equilibrium Green's function, and essentially derive the rate equation for this equilibrium Green's functions. But this approach is much more complicated. But nevertheless, the power of hydrodynamics is that the equations that we are obtaining, they should preserve almost the same form. The question will be what is the value of parameters, what is the value of constants that we have in these equations. And this, of course, might depend on the way of the derivation. But I'm quite sure that qualitatively we will have a similar theory with the same parameters present there.
Thanks a lot.
Okay, Mandela Mahirin.
Hello, thank you very much for the interesting talk. So my question was on the thermal gradient that appears in the currents, and I think also in the chiral currents in one of the slides. Yes, here. So I have two questions. One is this somehow related to the thermal Hall effect? And also the other question is, how would you expect this to generally influence the dynamics of the system? Thank you.
Yes, good question. So to answer the first part, I would say that no, because in the thermal Hall effect, one should have this term multiplied by electric field or chiral shift. So there should be some structure here, similar to this, for example, term. But instead of the electric field, there will be this gradient. And in Weyl semimetals, in principle, anomalous thermal Hall effect is possible. However, to answer the second part of this question, I would like to note that for systems where there is no external temperature gradient, the dynamical generation of such some thermal gradients will be negligible if the velocity of the fluid is small. So unless we are keeping our sample explicitly heated, then I would neglect these terms in the derivation of flows and even collective modes. But if one considers this as an external force, then in principle it can be present and plays a role of some kind of effective electric field.
Okay. Mandela, that's okay with you?
Yes, thank you. Okay. I just have one quick question too. Would you also expect this term to appear in, for example, an astrophysical context? Because in high temperatures, I guess it could play a role.
I would assume that yes, it should appear because the presence of the terms in current should not be based on the fact that whether the system is solid or some fluid. However, the dependence of the thermal conductivity, the thermal conductivity coefficient might be quite different in systems. So I would suspect that the difference would be quantitative rather than qualitative.
Okay. I don't see any additional questions coming from the audience. So I would like to use this moment to thank the speaker again. Thanks everybody who made the time coming to the colloquium. We will be wrapping it up. So unless in the next 1 or 2 seconds somebody wants to ask a question, we will be wrapping it up. Thank you, Pavlo.
Thank you again for the possibility to present this talk.
Okay.